Hello, this is the second part of the chapter 4.8, and we will talk about linear difference equations. In the previous part, we discussed the signals, which is just digitized functions, and we try to organize in a multiple different ways. And the easiest way so far is what's called a linear difference equation, which is just a linear combination of our signal y over the steps from k to k plus n multiplied by the weights or scalar from a0 to an. And the right-hand side would be equal a signal zk. And in terms of our sound example, we can look at this linear difference equations as, like the linear combinations of for each frequency. For example, if we have a frequency, say 20 hertz, we write it down as the sum of intensity at 20 hertz for the time moment 0, 1, 2, and all the way to the n seconds from the beginning. And this is a very common way to keep the what's called digitized data or digitized time series. Okay, let's just practice a little bit more with this notation and let's try to solve this kind of equation. Of course, we're given an equation, we would like to solve it. And we are given this homogeneous difference equations. And the easiest way to solve it is try a substitution as y, our signal k, is equal r some number to the power k. A lot of the digital linearized equation has a solution in this form. All we need to do is find specific number for our parameter r. Okay, let's just substitute r to the power k and let's see where it will lead us. And we will just substitute instead of the y in the power k3, our parameter r to the power k. And here is because our index become the power, all we do is just transfer our index up to the power. So then we take to the second part, so we have -2 times. Again, we substitute our index for the power, r to the power k plus 2. Repeat for the third time, -5 times r, and now power is now k plus 1. And finally, yk will give us r to the power k. And of course, it's equal 0. Okay, so now we substitute our supposed solution. Let's try to solve it. An easiest way to approach would be just start by factoring out r with the lower power, which happens to be k here. So we factor out r to the power k. So what do we left? We left with a third degree polynomial, cube from the first term, second from the second term, one from the r from the third term, and the free term 6 from the last one. So now we have a third degree polynomial, so we can try to factor it out. And here we are pretty lucky because our zeros are pretty simple. The first equation will give us 0r is equal 1. The second equation will give us r is equal -2. And the third one is equal r is equal 3. So we have actually not one, but 3 potential solutions for this equation. So each one of them should work. So the first will give us r equal 1, give it 1 to the power k. The second will give us -2 to the power k, and third will give us 3 to the power k. And all 3 of this is the solution to our difference equation. But don't trust me just like that. I think we should at least once try to confirm that these numbers would get indeed a solution of difference equation. How we can verify it? Plug it back into our equations. Instead yk plus 3, we will use our 3 to the power of the index k plus 3. And then we repeat for the 4 other terms, and it should give us 0. And again, let's try to factor out 3 to the power k and see what's left. So first term, say that what left is 3 to the power 3 or 27. The second give us 18, and so on so far. And if you try to add all this number together, you will notice that you will get a good 0, which means we started from 0, we end at 0, which means that our 3 to the power k indeed a solution of our difference equation. And you probably notice this neat trick I keep using when I keep factoring r to the power k. That's actually a very common approach to dealing with difference equation. And we generally say that our r to the power k satisfied a homogeneous difference equation when our r is the root of what's called ancillary equation. So when it's equation when we factor out r in the lower power n. Okay, this is all for this part of the chapter. So now I'd like you to go to the end of the chapter and practice by solving a couple more of the linear difference equation. I know you will be uncomfortable first, but believe me, if you invest a little bit in them, they are fun to solve.